In the last video, we have discovered that quantization of angular momentum leads to an angular speed 5h bar divided by 4 mass of the electron, capital R square. Now we will consider part A, which is the case where we have a uniform charge distribution. Total charge of the electron is distributed uniformly over its surface. Okay, so the uniform surface charge density I'm going to call sigma. Okay, and the electron charge is minus E, so this will be distributed over the surface of the sphere. The surface area of a sphere is 4 pi capital R square. Then we can calculate the charge on an area element. Then the charge on an area element dA is going to be dQ, which is sigma multiplied with dA. Now sigma, the charge density, is minus E, electron charge, divided by 4 pi capital R square. Electron charge, remember, is 1.6 10 to minus 19 coulombs. And as for the surface area element, if we look at our calculation in the previous video, it's R square sine theta d theta d phi. That's our area element. So we're going to substitute that here. This is multiplied with capital R square sine theta d theta d phi, and the capital R squares will disappear, and we will be left with a differential charge dQ minus E divided by 4 pi sine theta d theta d phi. So it's independent of the radius capital R. Okay, now we can calculate the current due to this charge. Then the current due to dQ will be dI. So dI will be this charge dQ completing one turn in a period capital T. So this is basically minus E divided by 4 pi sine theta d theta d phi, and for the 1 over the period we can substitute V divided by 2 pi R sine theta. So V divided by 2 pi R sine theta. V is our tangential speed. So we have talked about this before. We have the tangential speed V is equal to omega R sine theta, which is also equal to 2 pi R sine theta divided by the period. But this was for the solid sphere. For the case of the surface charge, this will be replaced by capital R sine theta. So we have this charge element moving on this circle, completing this circle with radius capital R sine theta in one period. Therefore, it moves the circumference of this circle 2 pi R sine theta divided by t, which is our the tangential speed. Okay, so you can see that the sine thetas will disappear in that case, and we will see that the current contribution to the current due to this charge element can be written as minus EV divided by 8 pi square capital R d theta d phi. Okay, so this is our current due to dq making a complete turn in one period in the circle with radius capital R sine theta. Now we can talk about the area enclosed by this current. Okay, so the area enclosed by this current dI is going to be the area of the circle with radius capital R sine theta. So it's pi R sine theta square. So this allows us to calculate the contribution to the magnetic moment from this current. So that is d mu, because dm was for the mass element, d mu is for the magnetic moment. That is the perpendicular area multiplied by the current, the SI definition of magnetic moment. So this gives us minus EV divided by 8 pi square capital R multiplied by the area pi R square sine square theta. Now you can see that the R square will get rid of this R. So let's do it this way. This R will get rid of the square. And we will have pi getting rid of this square. All right. And this will simplify to d mu equals minus EV over 8 pi. The R in the denominator disappeared and pi square has become pi, and we are also left with an R on top and sine square. Of course we have in di d theta d phi, so we have to put that here. So this will be sine square theta d theta d phi. So that's the contribution to magnetic moment from this charge element creating a current dI enclosing a loop with area pi r sine theta parentheses square. So this is the okay, so let's move this here. So this is the differential magnetic moment. It's the contribution from dI. Now we have the tangential speed. V is equal to omega times capital R times sine theta. So we can substitute for omega our result from the previous video, 5h bar over 4 mer squared. So this is 5h bar over 4 mass of the electron capital R squared multiplied with capital R sine theta. So this will get rid of one of the r's in the denominator. So this is basically 5h bar divided by 4 mass of the electron capital R sine theta. So this V we can substitute to the d mu equation. So this is to be substituted to d mu expression, then we can write d mu as, so we have minus er over 8 pi to start with here in front of v. So we have minus e capital R over 8 pi. For v, we substitute 5h bar sine theta, 5h bar sine theta over 4 mass of the electron capital R, and then we have sine square theta d theta d phi. Okay, so we have substituted for v this result. So this is our d mu, and you can see that we have some simplifications here as well. So we have an r on top and r at the bottom, so these r's will disappear, and we will be left with the following result for d mu. So let's write this in terms of Bohr magneton, minus EH bar divided by twice the mass of the electron, EH bar twice the mass of the electron. Then, so we have utilized one of the 2's here. We're left with a 2 here, 2 times 8, 16. So this will give us 5 divided by 16, 5 divided by 16 pi, and then we have sine theta and sine square theta, so that will become sine cube theta d theta d phi. Okay, so all the terms are taken care of. EH bar divided by 2 mass of the electron multiplied by 16p, and then we have a 5 on top, sine cube theta d phi. Okay, so this is our contribution to the magnetic moment, d mu. And here we have done this in order to introduce the Bohr magneton. Bohr magneton is EH bar divided by twice the mass of the electron. Okay, now we're ready to write the total magnetic moment, so we will integrate over all contributions on the sphere. Then the total magnetic moment mu is the integral of d mu over the surface of the sphere. It's an integral over phi from 0 to 2 pi and theta from 0 to pi. We have, as you can see here, 5 over 16 Bohr magneton with a minus sign, sine cube theta d phi. So we have minus 5 Bohr magneton divided by 16 pi sine cube theta d phi. And this will give us, if we perform the phi integral, minus 5 divided by 16 pi multiplied with 2 pi. That's the phi integral. So let me rearrange this. I'm performing the phi integral first, and then the theta integral. So this limit will be 2 pi, and this limit will be pi. So performing the phi integral first, I have minus 15 over 16 pi multiplied with 2 pi Bohr magnetons, integral from 0 to pi sine cube theta d theta. And this is going to give me 2 pi. Will get rid of this 16 pi and make it 8. So minus 5 over 8 Bohr magneton, integral from 0 to pi 1 minus cosine square theta sine theta d theta. And this we have performed several times. We can recall that the end result is 4 over 3. So you can recall this from the moment of inertia calculation, from IZ calculation. Okay, so we're recalling this result from IZ calculation. Okay, so with that, the total magnetic moment will become minus 5 over 8 Bohr magneton multiplied with 4 over 3. And this 4 will make this 8 2. So the end result will be the total magnetic moment is minus 5 over 6 Bohr magneton. Okay, so as you can see, it's not one Bohr magneton, it's 5 over 6 Bohr magnetons. The minus sign comes from the electron charge, the sign of the electron charge. Okay, so we have done part A of this problem. We're trying to calculate the magnetic moment due to spin in units of Bohr magnetons on the assumption that the total charge of the electron is distributed uniformly over the surface. The surface charge density is charge of the electron divided by surface area of a sphere, 4 pi r square, and sigma dA is the charge of the area element dA. So if we look at an area element here, dA, this area element has area r d theta r sine theta d phi, and this area element is rotating on this circle with radius capital R sine theta. So we have multiplied sigma with dA to calculate dq, the charge contained in that area element, and the current contribution to current from the dq is dq divided by the period t. So this is going to give me a current minus EV over 8 pi square r d theta d phi, where I have basically written for the period. So this t is the period. The tangential speed v is 2 pi r sine theta, which is the radius of the circle. So that's the circumference divided by the period. So with that current contribution, I look at the area enclosed by this current, which is pi times capital R sine theta parentheses squared, and calculate the magnetic moment of that current loop. So this current loop produces a magnetic moment, the current that flows multiplied by the perpendicular area. With the right hand rule, you can see the area vector points up. If the current is flowing like this, the area element points up, the area vector points up, so it's a perpendicular area, which is basically the area of the loop. So I multiply this current di with the area of the loop, pi times capital R sine theta parentheses square. That gives me d mu. And for the tangential speed here, which is omega times r sine theta for this area element, we can basically substitute the result we found for omega using the spin angular momentum quantization condition. So basically we have this result for omega here, 5 h bar over 4 m e r square, which is saying that the angular momentum is quantized in units of h bar. H bar over 2 is the result with the spin quantum number s equals 1/2. And this gives me a magnetic moment contribution here with V substituted as omega r sine theta, omega result that we have obtained before. And this d mu that we calculate, we can write it in terms of a Bohr magneton, which is EH bar over 2me. And then we can integrate this over the full surface of the sphere in order to calculate the contribution from all current loops. So this current loop, this current loop, this current loop, this current loop, etc. They are all contributing to the magnetic moment. And this integral from 0 to 2 pi of the phi integral gives me just 2 pi. 0 to pi sine cube theta d theta integral we have performed several times. It was equal to 4 over 3. So we can substitute that result here. So we find that the total magnetic moment due to surface charge uniformly distributed on a sphere is minus 5 over 6 Bohr magnetons.